Okay, I just wanted to share with you a few more animations or videos that might illustrate what's happening in the plate tectonic world here. So prior to all the cool tech that we have today, when Wegener was trying to puzzle out what was happening, they didn't have the luxury of having the view like we do here in this video. And as I play this video, what it's plotting is earthquakes, and it's starting, I know some of the stuff is small, but it says, what, 1965 down there? So it's plotting from 1964-ish to the present, or pretty close to it. And so it's also plotting magnitude, depths. It's even throwing some volcanoes in there. And so you could see that there certainly is a lot of data here. You know, up to the top, there's some numbers there. It's in the hundreds of thousands of earthquakes that are being plotted here. So we know that this data can tell us something about boundaries, because we know that where plates interact, we should get lots of earthquakes. And over time, when we look at something like this, it might seem obvious. Now, previous, of course, we didn't have this information. So scientists and geologists trying to puzzle out, what all this stuff meant. We knew there was earthquakes and volcanoes. The pattern wasn't really clear. Now, after the fact, of course, we can look and see that there is some type of pattern here. It's a little hard to see with the tiny dots. So let's see, I've got a better image here. So here's one where the dots have been enlarged. It's kind of the same program. But you can obviously see there's some type of pattern here. Does that mean that every earthquake follows a pattern? Well, no. So there's some weirdness kind of out in here. But overall, there is some pattern here. And that pattern is actually the plate tectonic boundaries. And so earthquakes are caused by stress of the brittle lithosphere. And so where the stress is the greatest is where these plates are interacting, whether they're pulling apart at divergent boundaries, colliding at convergent boundaries, or slipping past each other at transform. The stresses are greatest here. And so it's kind of outlining our plate boundaries here, which is pretty cool. And there's also a correlation that we can see, not just between our earthquakes, but between our volcanoes. So if I jump to this slide here, you can see hopefully that as we go back and forth, there's kind of a connection here. Not everywhere, but where we have earthquakes, we also have some patterns that suggest there's some volcanoes here. Now, every boundary does not produce magma that can lead to a volcano. Said only certain types. So transformed, we shouldn't get volcanic activity. There's no process for making magma. But where we collide and have subduction, we would expect magma. Where we pull apart, we would expect some magma. And so at places where the two continents collide and there's no subduction, we wouldn't expect that. So we could argue that if these are boundaries here and we look at some volcanic information, there's some suggestion that maybe there's some subduction happening here. And so that is, the volcanoes might be telling us that. So certainly here and here and here and here, over here a little bit. Now, of course, there's other ways we can get volcanoes or older volcanoes, so it's not always 100% accurate, but there's certainly some connection here that we can see. And the last thing I'll point out with the volcanoes is the colors here are also indicating depth. And so there are places where we see deeper earthquakes. And so there's a suggestion here that the deep earthquakes are caused by subduction. Because the argument is that the oceanic crust is relatively thin, the lithosphere, maybe 20 to 50 kilometers. We wouldn't expect any earthquakes below that depth because below the lithosphere is the asthenosphere, which is ductile, squishy, plastic. It doesn't break and fracture like the brittle lithosphere. So if there's nothing weird going on, then we shouldn't have any earthquakes in the oceans that are deeper than, let's say, 50 kilometers. Even though the continents are thicker, there's still a certain depth at which we wouldn't expect to see any more earthquakes because that's the thickness of the lithosphere. But we do see really deep earthquakes. So how can we accomplish this? The idea is that we're taking a very brittle lithosphere and we're pushing it down deep into the asthenosphere. And the asthenosphere, because it's mushy, ductile, can move out of the way. And so it allows this brittle piece to go deeper than the thickness of the crust, and we end up getting earthquakes that are deeper. So these deeper earthquakes are another indicator of subduction, a collision where one plate is being pushed beneath another. And so lastly, I'll show you this. So here's a quick little animation where there's a plate boundary here between these two kind of islands. And if I get this thing rolling for you here, it's doing the same thing the program previously did. It's plotting earthquakes, and it's also plotting depth. And so now these aren't super deep, but they're still showing that pattern that we think about when we see two plates collide. So this is a convergent plate boundary right here. And what's the pattern that we see? We see that deeper earthquakes are occurring to the left here. So there's a boundary that runs kind of here. And so what does that mean? You should be able to puzzle out with using the depth of the earthquakes as to, if I tell you that this is a boundary right here and these two plates are colliding, which plate is being subducted? So if you think about it, this plate on the right is going down underneath this plate on the left, causing deeper earthquakes to occur over here. So if that's not super clear, let's see if this helps. So here in theory would be something similar to that, where you're plotting the earthquakes, but now you're looking at a side view. And the idea here is the earthquakes are kind of showing you the lithospheric plate. It's up here, has a certain thickness, it runs into another one, and it's being pushed down into the asthenosphere because this material can move, it can flow. This is brittle. I push it, this goes out of the way, but the brittle part here is under lots of stress and it breaks, and the earthquakes occur here and not here. This is the non-brittle part. And so when we see subduction like this, this is the pattern that we see, and it's nice that now that we have some better technology and we can plot these things and have some cool graphics, even though I know this one's pretty old, it reinforces these ideas that were put forth in the 60s when that idea of plate tectonics first came about. So hopefully these little kind of animations and pictures maybe clarify some things for you. And so in addition to looking at the PowerPoint, hopefully this will help you understand some plate tectonic stuff.